I would like to thank the scientific committee for the honor of this invitation to give a foundational lecture. I kind of regretted to take this challenge and to have to speak between two giants of Bayesian statistics like Peter and David. So let's see what I managed to do today. So I said it's a subjective tour that started from this motivation. So I was thinking, what should I talk about in this lecture? And well, somehow it's a reaction to something that I hear more and more often, even from Bayesian friends, saying things like, I'm agnostic about Bayes, I just use Bayes as another tool, or I use whatever works. Well, it's not only my sample. Apparently, Steve McKeekern, ISBA president this year, has similar sample. In a bulletin, he said, sample of views have heard this Bayes is merely another tool, or sometimes Bayes is equal to shrinkage, and the opposite, Bayes is magic, which is also not good. So what is this? Okay. So I understand. I mean, I can understand some reasons for saying that. No, we want to see Bayes in action. This light is terrible. We want to see Bayesian solutions of difficult problems, so we don't care so much about what is behind the foundations of probability and Bayesian statistics. But still, this is a foundational lecture, and I thought I couldn't resist in trying to give a sort of reaction to this attitude and maybe have some discussion or reactions from you. And my point will be that the interpretation of prediction, that probability and prediction that we take is in fact not neutral and changes our viewpoint, focus, and interest. And we know this, we've been saying this, sometimes we forget, we remember again. And there are many ways one can argue about that. We know discussion of p-values or model selection also. But I will try to argue about this so that what interpretation of probability we take makes a difference through my subjective choice of topics. So I will do a little premise and then start with the basic Bernoulli trials and Poilievre-Wurz, and then mainly I'll talk about notions of exchangeability and reinforced processes to go to something that is closer to what I have been recently doing on randomly reinforced processes. The last point will be just a little open conjecture. I'm not sure it makes sense, but I would like to mention. And don't kill me that we are in the world of data science, big data, and so on. I'm talking about a little bit of history. But for a moment, let's spend a few minutes just thinking back of the historical background environment where people among the founders of modern Bayesian statistics, people like Ramsey, Savage, De Finetti, worked and lived. So for a moment, forget we are in the data science era. Let's go back in time to the 1920s, 50s. And my consideration is just that it perhaps is not a coincidence that these founders were mathematicians, logicians, probabilists, that were also involved in concrete problems, difficult and concrete problems in actuarial science, economics, information, risk, and decision. So, not very technological slide, I see. Picture, so we are back, Cambridge in the 20s. Ramsey was born in 1903 and died at only 27, too young, in London. Ramsey was at Cambridge. Imagine the 20th center of knowledge, the place where economists like Piero Sraffa and John Maynard Keynes were living. So Ramsey starts his Truth and Probability that was written in 1926 and published after his death, arguing on Keynes' vision of probability. So he's now interested in logic as the science of rational thoughts and looks for a notion of probability and decision in this perspective. De Finetti was born a few years ago this day. Happy birthday to Bruno De Finetti today. So De Finetti was a mathematician, but initially worked at the Italian Central Statistical Institute and the Assicurazioni Generali insurance company, very important insurance company in Trieste. So the problems he was facing were actuarial problems, life insurance, credibility. And De Finetti did write about economics. Here, I don't know if you can see, but it's his work, Il problema dei pieni, that scooped the work of Markowitz, for which Markowitz got a Nobel Prize. So he was doing important work in this kind of problems as well. And Ramsey, well, you see there is the war. So we had the Second World War. We're moving from the old Europe to the US, a center now, at least for some part of the war, become the US. Jimmy Savage, well, he was initially, worked in several places, initially at the Institute of Advanced Studies at Princeton, where he was interacting with people like von Neumann and Milton Friedman, later Paul Samuelson again, from decision theory and economics. And I put a war also to remember that this little picture of the war, to remember that it was during the war and at the end of the war that Abraham Wall developed his theory of modern statistical decision theory and sequential analysis to speed up experiments, sequential design, sequential analysis. So I finish with this little history, but I thought that since we are somehow, despite we are Bayesian, but we are used to probability and frequency, if I had said at the beginning, let's think of probability as a tool for measuring information, risk and decision, maybe it was too different from what we are now used or still used. So this way you see that we have another vision of probability, not as frequency, but really related to problems of prediction, risk evaluation, decision. So it's just to underline this change of perspective. A too short summary of Savage work, Savage was starting from actions. From actions, the people, like human being, a human agent, take decision, take action, we can order the actions, and from then understand. So if the same was example, if I take the umbrella or leave the umbrella at home, underlines my probability, beliefs, probability, and utility about holding the umbrella among the two actions. This doesn't mean, of course, that the relation between probability and frequency is not fundamental. It still remains fundamental. And this is just, to start with changing entering in this perspective. Probability as related to prediction, risk, and decision. And I would like just to mention that maybe because I work in a school of economics, I'm surrounded, that I like it or not, I'm surrounded by economists. So there is indeed active research still along the lines of Savage work, this kind of work. So I mentioned just 2 Nobel Prizes, Sargent and Sims in economics. And it's a bit weird, I find, that we Bayesian kind of forget about this. So I wanted to take this opportunity of the foundational lecture to just mention this. And indeed, I am happy to see that even, in fact, there are recent works on modern problems like intractable likelihood and high-dimensional applications, data that, in fact, start from, seems to take this decisional approach back. So after this introduction, let me go to a bit more, little example in probability. So I said I want to talk about notions of exchangeability and reinforced processes, but also I want to do this again, underlying how the way we look at these problems, depending on our interpretation of probability, can change our viewpoint. So I start with this basic example, Bernoulli trials, experiment is sampling with replacement from a 2-color rune with a known composition, and I think any Bayesian statistician would agree by saying, okay, the statistical model IID Bernoulli given theta and theta usually has a conjugate beta distribution. This implies that the probability of picking one is given by alpha 1 over alpha, the initial Urn composition. Alpha 1 is the number of white balls, alpha the total number of balls. And then the predicted probability of 1 is the number of white balls, the Urn composition, the number of white balls in the urn at step n divided by the total number of balls in the urn. But this is the probability law of a sample from a polyurn, what I just wrote. So my question, if we don't care about the interpretation of probability, how comes that we use a polyurn to describe a Bernoulli urn? Answer? The physical experiment is Bernoulli urn, sampling with replacement, but we use a polyurn to describe it. This polyurn is a basic example of a process with reinforcement. We all know how it works. We have an urn that initially has alpha balls, alpha white. At each step, we draw a ball and record its color, and then we return the ball in the urn together with another ball of the same color. So this, I said white and black, and this is red and black, but this is an evolving process. So Edberg and Polya in the 1923 introduced this model for many reasons, but in particular it can be a model for the spread of contagion. And the interest is what happened of this contagion, what will be the limit fraction of white balls, say healthy people in the population. And well-known results is that the proportion of white ball converge to a random limit. So the surprise here is that the limit is random. And of course it's random because it's a theta of little omega, because it depends on the little omega that is, it depends on the history of our drawings or how the contagion spreads, and has a beta distribution. So that's a polyurn. So we should use a polyurn for modeling an evolutionary phenomena such as the spread of contagion. And if we take it this way, then we should do Bayesian inference, perhaps, on the spread of contagion. So on exchangeable data, because this data happen to be exchangeable, but not for Bernoulli. So what happens is that in a polyurn, the sequence of colors turns out to be exchangeable, and then by the magic representation theorem, this evolutionary spread of contagion is probabilistically equivalent to a static experiment where we pick an urn, so we pick an urn composition theta from a beta, and then we sample IID from that urn. So the process is evolutionary. It's just a property of exchangeability that makes it probabilistically equivalent to static sampling from an urn with random composition. And if we take, so why are we using the polyurn to describe a Bernoulli urn? It's because we take subjective probability. And the polyurn is not a physical description of this phenomena in a way. It's a description of how we learn. It's our learning rule. So the process, the experiment is static, but we learn from experience. So the contagion of disease is in fact a spread of information. So is the rule is our learning rule. And we are saying that observing a white ball reinforces our prediction that the next ball is white. And then by exchangeability, we have the hypothetical model that we are familiar with. So you see that it does matter what interpretation of probability we give. If only we accept that probability is our subjective description of the phenomena, the little in our mind, we can use the polyurn scheme as a learning scheme for Bernoulli trials. Probability and frequency, of course, we don't quote this little sentence from Ramsey, truth and probability. We want our beliefs to be consistent not merely with one another, but also with the facts. And so if again, we have the two possible interpretation or uses, not contrasting. Of course, a Bayesian can be interested in spread of contagion, of course, as well. If we if we're dealing with the spread of contagion, then the main interest is in the urn composition, and we saw that it converges to the random zeta, there's a beta distribution, and we may be interested in results, to say a bit more, to refine this result with central limit theorems for the scale difference between the Urn composition and the limits. Notice that, as these things are well known, but I understood the foundational lecture is really kind of overview of known things in my view. And so it's a random rescaling. We seem to suggest the usual central limit theorem, but theta is random. And so roughly it means what is written. It's a conditional convergence to the normal. If instead we take a subjective, we look at this Polya-Urn scheme as a subjective learning rule, maybe the focus of interest may change because we may be interested in comparing, well, of course we are interested in results as before, but we are also interested in comparing probability and frequency. So maybe we want, well, it's also true, we know for the Polya-Urn that the frequency also converges to the same limit as the predictive, as the composition zeta n, and the central limit, and we are maybe interested in central limit theorem and now compare the frequency, say the prediction zeta n and the frequency. So how far our prediction are from the observed frequency, but also give central limit theorems about this, or central limit theorems about this prediction error, our prediction zeta n. Okay, our prediction zeta n and the next observation, prediction errors. I've been thinking if these results could be about Bayesian counterpart to frequencies asymptotics. Don't have, so maybe that's my view. I think they could be, and the fact is that also these results are stated almost surely with respect to P, and P is changeable probability law of the sequence Xn. So it's not with respect to a true model respect to P. So maybe we could be unhappy about this, but I would like to mention that people have tried to go further. I would like to mention this important work by Diaconis and Friedman, who indeed gave a result for a cave dice that goes in this direction, in my understanding, that reformulates the usual statement, frequent is consistency, the posterior pile-ups around the true value, almost surely pitted at zero infinity, replace it with finite sample results without exceptional null sets or true value of the parameters. The results is like that. If we consider again a dice this time, and we consider an interval centered in the frequency, oh sorry, this is, I think I reported for the coin. So we consider an interval plus h minus h around the frequency, then the posterior odd of being inside the interval against being outside is bound, as is bound. And the right-hand side, the term doesn't depend on the sample, so this is an inequality that holds for any x1, xn, so there are no null exceptional. That is not an almost surely with respect to p. It's for any x1, xn. And the observed fraction stands for the true parameter. Well, it depends on the sample through n. So that I said that this is a subjective tool, but I'm not going through an highway. I will have a sort of deviation. So this is a kind of a first deviation from my route of Ursen. So I think that's my comment in my deviation, that there is still work to do on finite sample properties of Bayesian procedures. Efron recently wrote about frequentist accuracy of Bayesian procedures, but I insist that I would like to keep in mind that the interpretation of probability is not neutral, and I would like to take my interpretation of probability, otherwise I don't understand why I use Polya-Urn for Bernoulli-Urn, and keep thinking somehow. I mean, people have been thinking about these kind of problems since ever, but I think there is still work to do. I just, evaluation of forecaster, scoring rule, merging on opinion, some notion of, is my Bayesian procedure exploiting the information I have, or do I have good information, in other words? And I just, some posters by Stefano Rizzelli and another poster by Sarah Wade and Michele Peruzzi somehow will go in this direction. So going after this detour, taking again the highway of the polyaurna. Well, polyurna is an example I like because it's a basic example of a predictive construction of an exchangeable sequence, where the steps are: we look at first we express a probability on observable facts, not on parameters. And here, if we have a sampling with replacement for an urna, we say we can accept it to say the observations are exchangeable, order doesn't matter. Then we do another step, we express a predictive distribution, and the sequence of predictive distribution always characterize a probability law under very mild conditions on the process, and under some conditions, this probability law P will be exchangeable, and then by the representation theorem, we have the equivalence with the usual model and prior, the sequence of empirical distributions, which is the analog here of the urn composition from the urn, polyaurn to color polyaurn, converge to a random distribution F. It depends on the little omega in our mind, independent interpretation, which is called terminology of Aldous, the directive measure, and the data are a sample. So I pick an F, and then I sample IID from F. And I'd just like to mention that notions of predictive sufficiency have been studied. So results of the kind, if I think that the summary of the observations Tn, say, is sufficient for predicting the next one, then the limit of that Pn under condition will go to a parametric directive measure. So I can index the directive measure through a parameter that will be the limit of the sufficient statistics under conditions. Just mention this because now that we have big data and we want to somehow, since either we improve the computations or we try to simplify the models, I'm trying to suggest obvious story to try to maybe reason on predictive sufficiency. Maybe we don't need all the data there. So I will hurry up now. The polyaurn, I said, is an example of a predictive construction based on processes with reinforcement, a beautiful review in probability surveys by P. Mantle. And the most famous immediate extensions are in a urna of K colors, and we know by Johnson sufficiency, if we accept a Johnson sufficiency postulate, and we say that the frequency of color J is sufficient for predicting the probability that the next ball will be of color J, then the predictive has to be of that linear form, and that characterizes a Dirichlet distribution as the prior for the exchangeable sequence. And extending to countable colors, we have polya sequences, Blackwell and McQueen 1973, where again, where we can extend, we say sort of extension of Johnson sufficiency postulate arrive to this predictive rule, where that on the next observation may be either a new value from F0 or come from the empirical, and again, then X is exchangeable, the sequence Xn is exchangeable. The predicted distribution converge to a random F, which is discrete, and it's a Dirichlet process. This I mentioned for as the most famous. I just take one little deviation, but not too gasoline. We have to take the predictive distribution seriously. So it's very natural to say the predictive is a weighted average, as here, between my prior guess F0 and the empirical distribution. But we are saying more. We are saying that the next observation can be a null value with some probability proportional to the frequency, or a new value sample from F0 with probability that depends on that constant alpha, which implies size in the sample. And so the sample, in fact, is described by a random partition that says which value is equal to which value, and then by these distinct values, the sample centroid or species, And Antoniak in 1974, just after Ferguson's paper in 1973, noticed the importance of this discrete and discreteness implication, the implications of discreteness of the Dirichlet process. Compute the probability law of the random partition, which, as you see, is very parametric, depends only on alpha, k number of distinct values, and n. And when considering a slightly different way of expressing the partition, this is the celebrated Ewing sampling formula, Ewing's 1972. And just mentioning this to say that predictive construction, also maybe now you are a bit sleeping and say, what is she talking about? It's indeed a very rich approach, a very fruitful approach. And just have this slide to say, just thinking it's not only Bayesian non-parametrics, but Bayesian non-parametrics is indeed the basis of many developments. My impression is that it was perhaps because of this common predictive approach that we had the impetus, the growth of fresh and sound constructions from the machine learning community in Bayesian non-parametrics more than 1 decade ago. These predictive distributions are seen as generative algorithms to generate sequences, and then people even can propose this generative algorithm, even forgetting about what is the prior implied. So just give the predictive or generative algorithm. And I think a beautiful example is the Indian buffet process by Griffiths and Garamani, where they gave the algorithm, they gave the predictive rule somehow, and the Finetti measure was only found prior, was only found later. On the other hand, it's not, I mentioned the Ewing sampling formula because that's a very well famous, celebrated formula result, a beautiful result. That is a beautiful example of how, I said, interdisciplinary cross-fertilization, so it has applications and impact in many, from evolutionary molecular genetics, population dynamics, neutral theory of biodiversity, combinatorics, and so on. And so it's not only, of course, Bayesian non-parametrics, but it's a cross-fertilization of ideas from different fields. So this predictive approach is fruitful. On the other hand, of course, it's not only the Dirichlet process, and I just 3 remarks here. Clustering structure of the DP is quite parametric, as we have seen, and lacks power law behavior. Kingman, 1978, beautifully explained that. And I'm just giving references, not entering in any details. And so we need extensions. Perhaps the most somehow beautiful is the 2-parameter Poisson-Dirichlet, but classes of completely random measures. And I mention here not only a review, it's a discussion in this paper. But going ahead with the predictive approach, we can think of Walker and Mulliere gave a characterization neutral to the right processes via an extension of Johnson's sufficiency postulate. I have to say that, of course, what we are saying through Johnson's sufficiency postulate, that the probability that the next observation is in a set A only depends on the frequency of that observations in that set A is clearly restrictive if we have continuous data, because we would like to spread information carried by the frequency in A to neighborhood sets. And I think this can be a predictive motivation for smoothing of the Dirichlet process through mixture models. We could consider smoothing the predictive distribution of the Dirichlet process so that the frequency in a set gives information about the frequency of neighborhood sets. I mentioned, so the story was what approach we take makes a difference, or at least we should be clear about what is the physical experiments that we are facing and what are our statements, perhaps in making our assumptions in a predictive way. I mentioned some exchangeable constructions, and of course we have more complex dependent structure in the data, so We may want to look at notions of partial exchangeability. Exchangeability is invariance under any permutation. Partial exchangeability roughly is invariance under a subclass of permutations. And maybe the first notion was due to De Finetti, partial exchangeability in the sense of De Finetti, when we have multiple experiments, for example, a sample of patients in different hospitals. So we have more, and the array, so the samples from different hospitals, say, is partially exchangeable if its probability law is invariant under separate finite permutations of the row on the column. So in a way, we can, the data from each hospital, the sequence from the different, from each experiment is exchangeable, but the sequences are not independent, and moreover, they become asymptotically independent if we can observe the infinite sample. Important notions, I'm going to go back to that, are Markov exchangeability. They also, Diaconis and Friedman, or separate row column exchangeability, on which I return in a moment. So this is just to say that people have taken, following this predictive construction, have proposed interesting processes for partially exchangeable sequences or arrays. So here is just mentioning some important construction, the Coppersmith and Diaconis edge-reinforced random walk on a graph, where we have a graph with different vertices, and there is a random walk along these vertices, and an edge is reinforced when I cross it. And this has many implications, and here we may be interested in the fact that this edge-reinforced random walk characterize conjugate prior for the transition matrix of a reversible Markov chain. So again, is a predictive construction that characterizes a Markov exchangeable probability law for the process, and implicitly also characterize, here also explicitly, the prior distribution, and this prior distribution is conjugate. Muller and Walker, Muller and second Walker introduce the beta-Stacy process that had so many applications in Bayesian non-parametric survival analysis. Somehow the other phase of the beta process of Hjort on the distribution function and on the survival. And so they also have a predictive construction through a system of reinforced Urn processes that generates a Markov exchangeable sequence. Then they look at the sequence of the X0 blocks, which is exchangeable, and so the probability law, or the prior of this, or the directive measure, if you want, of that exchangeable sequence of lengths of X0 block is as a prior that as distribution that is called beta-Stacy process. And also these generative models have been proposed by Bell, Garamani, and Rasmussen. They construct a very sound hierarchical Hoppes urn. So we have, again, it's a predictive construction where when you need to generate new colors, sampling from an urn, from urns, we generate them hierarchically from another oracle urn on top. Anyway, that's this construction is used for building an infinite hidden Markov model where we can have an infinite number of states. So if we are interested, if we want a hidden Markov model, we don't know how many states, we can let the number of states unbounded. And so this hierarchical open construction characterizes a prior distribution, a Markov exchangeable sequence, and the prior distribution on the transition matrix is a hierarchical Dirichlet process that has been proposed and formalized by 10 others. So those were just to mention three important constructions for generating, predictive construction for generating Markov exchangeable sequences. Yeah, I would like to say a comment on definiti partial exchangeability. So can we construct predictive, can we characterize prior distribution for definiti partially exchangeable sequencing experiments in different hospitals through a predictive approach? Of course, there are many proposals. So the hierarchical Dirichlet process I just mentioned is an example, or extensions to more general hierarchical Pitmanion and others. They had a huge number of applications, for example, in topics models, language models. Is it possible? As far as I know, no, I can't. So, I mean, I want to have some dependence. So I have patients in different hospitals. Maybe I have big data. I would like to have something. So all the constructions that I mentioned, even the hierarchical Dirichlet process, it's a hierarchical model, and I have, so the computations need Markov-Chain Monte Carlo, or need variational inference, or need some clever computational strategy. If I have something analytic, again, I can try to simplify my model and maybe deal with bigger data set a bit more easily. But I don't know about predictive construction that generates a partially exchangeable sequence. It's simple, so it's simple analytic and there's some prior. I don't care about what prior, at least I want to have the predictive construction. For example, an idea would be to say that Xn, Yn, so I have two hospitals and patients X and Y in the two hospitals, and one could say the pairs are exchangeable with a Dirichlet process on the joint, but that is too rigid. And it's a conjugate prior. Some improvement was done by Sarah Wade and Silva Mongeluzzo and me as defining an enriched conjugate prior using the notion of enriched conjugate priors for the exponential family. But still, I think this is something open, and I don't know if it can be solved, not even solved in the parametric case. There is work by Bacalado, Holmes, and Diaconis also that I think with the notion of approximate partial exchangeability, which is different but not too far from this kind of problem I'm mentioning. And in fact, if we think of some construction that on predictive construction, and we hope they could be partially exchangeable, well, unfortunately, they fail to be exchangeable. So think of, and then we go to last, so we said a little bit of history, notion of, probability in polyhorns in general, reinforced processes for building exchangeable or partially exchangeable probabilities and models in this predictive approach. Generalization could be to consider randomly reinforced processes. So now I have a predictive, I may have one, or I may have a system of interacting sequences. Again, I'm saying interacting, or, well, I take this comment for later. So we can consider a system of interacting sequences evolving according to a randomly reinforced scheme. So suppose I have a sequence, X1 as some distribution, and then we have a predictive rule that reminds the rule of the Dirichlet process. Say this would be interacting Dirichlet processes, but we have weights. So we don't, well, we have weights. So the presence of weights that could be known, evolving with time and generally random. But this can be a natural construction. So we have a system, you imagine particles or observations, and we create some physical interaction or probabilistic dependence by letting some contagion not only along one of population, but also across population. This could be a natural construction, but in general is non-stationary and not partially exchangeable. So I'd like to spend the last few minutes discussing what kind of processes are these, are extensions of the processes we saw, starting not with these general interacting sequences, but from a univariate case. So here I go back to the first slide on the urn, polyurn, 2 colors. Imagine now that the addition, the reinforcement is random. So every time we pick a ball, we observe the color and we return the ball along with a number Wn, say, of balls of the same colors. Wn may evolve a long time or be random. This process may be a spread of contagion, but the individuals may have a different resistance or capacity of being contagious or surviving the disease. So this process is not longer exchangeable. In fact, it's no longer stationary, and time cannot be ignored. It's a special family of generalized polyurns with diagonal replacement matrix. Maybe more, okay. And has many applications, for example, in adaptive clinical trials. So a more general version of the same spirit could be not to color, but infinitely many color possibly, but we still have a sort of weighted Chinese restaurant process where the probability of joining a table, and if we don't want to, so the probability of joining a cluster or a table, or it could be a node in a network, or being sick, but depends not only on the number of customers sitting at the table, but also on their weights, the influence, authority. And indeed, this class of models was introduced, studied, also expressed slightly differently by Bassetti, Grimaldi, Leisen as generalized species sampling model. And this is a general form, but we have to specify the distribution of the weights. Of course, the properties depend on how the random weights are defined. And so Airoldi and others, and Bassetti, Leisen, Airoldi, Guindani have studied Ottawa sequence, beta-Gauss sequence, where they specify the probability law of this W. And these are interesting processes because we can imagine all the applications of Chinese restaurant process, Lewis sampling formula, or Dirichlet process, and now introduce this sort of selection and competition mechanism through the weights. What kind of property have? Well, these processes are not stationary and in general, and so no longer exchangeable. So there is an interesting property that these sequences may have, though. And say in the above predictive rule, when I attach the weights, I would distinguish 2 cases. If the weight is 10, or 10. If the weight is independent on the color, but depends only on the drone, then the process satisfies a condition that is written there. So the probability of the next observation, or the probability of the next observation in case steps, predicted probabilities are the same. So in this sense, the sequences are conditionally identically distributed. It's interesting that this property is a sort of marginal spreadability property, and is equivalent to exchangeability. So this CID property and stationarity together are equivalent to exchangeability. In a way, what we are saying is that, well, it doesn't matter, I skip that. So there are some properties, I just don't go through this slide, but the story is that also these processes are not exchangeable. They preserve limit law of exchangeable sequences. So if we go back to my initial slides, we have the predictive distribution converge to a random limit, and conversions of the predictive implies the sequences asymptotically exchangeable. And then we can have, again, for example, central limit theorems for the prediction errors and so. So that's, these are interesting processes to study. So I said that there are 2, and this is when we have the reinforcement, the weight that doesn't depend on the color. If it depends on the color, this CID property, it's not exchangeable, the sequence, it's not CID, but still asymptotic exchangeability and other limit properties hold. I would like to mention that, so we have processes, we are again predictive construction if you want, where we have an evolution, but we'll say the spread of a contagion or the spread of information, 10 or 5? Okay, no, I'm done. Spread of information, spread of contagion, it's not symmetric. The past observation don't have the same weight. They have different weights. So if I meet a sick person, the probability that I get contagious, sick, is not always the same, whatever person. We have a selection, a competition. So again, we have, however, the asymptote. So what will be the limit on composition? What will be the limit population? So also these processes are not exchangeable. We can study their limit behavior, but the limit law, unfortunately, is not generally known. It's difficult to find, and of course depends on the structure of the weights. There is a result that I would like to mention, because in a moment I'll go to my last slide with a conjecture that will be somehow inspired by this result. So suppose that I have, if you want, I have a network, and I'm considering, instead of sick and healthy, I have nodes, vertices in the networks, and edges, and this preferential attachment scheme that I was describing as a polyaurn reinforced process says that the probability that picking or that the next node will be attached to an existing node depends on the degree of the frequency, the degree of the node. So if we consider this randomly reinforced processes, well, we are thinking that there is a competition, so that if I have this network, the capacity of attracting a node doesn't only depend on the number of friends I have at Facebook, say, but only on how authoritative I am, or I beautiful, or whatever. So introduce schemes of contagious attachment, preferential attachment, or learning, where we have these weights. And this theorem is saying that, of course, the limit behavior depends on how the random weights are constructed. So if we have a set of dominant colors or edges or tables in a Chinese restaurant such that the expected value of the attached weight is mu, bigger than all the others, then this tables, edges, or colors will dominate. And indeed, the predictive probability of picking that color, I'm thinking here of K-color, multicolor reinforced one, will go to 0 for the non-dominant edges, and all the predictive probability will eventually be concentrated on the set of dominant edges. So they will be the only one to survive. So I mentioned this work that I'm doing with Sandra Fortini. So we know we have exchangeability and definitive partial exchangeability. We have this randomly reinforced processes with this condition identity CID properties. So a natural question was to extend, somehow paralleling this extension from exchangeability to partial exchangeability, parallel this extension and go from a CID to a partially ID CID notion. And so with Sandra we have developed this. And again, I just mentioned that this notion we give is not just having dependent CID sequences, but we want it to be equivalent to partial exchangeability under stationarity. We give asymptotic results, central limit theorem for the frequencies or the joint frequencies, so it doesn't matter. So I, of course, in 5 minutes will not go into this further and last thing that I want to mention, but I just want to arrive to the conjecture I was mentioning before. I mentioned exchangeability, definitive partial exchangeability, Markov exchangeability, and another very important notion of partial exchangeability is Aldous-Suven-Kallenberg exchangeability, that is referred to an array of random variables, and we have notions of separate exchangeability if we can permute the rows and the columns, or jointly if we can permute the rows of the columns with the same permutation. There is a sort of similar analog of the definitive representation theorem for exchangeable sequences, also for row column exchangeable sequences. That is the basis of many statistical models for network, random graph, and so. Again, I knew I wouldn't have time to give any detail, and that would be, of course, maybe another foundational lecture for someone more expert than me. We had a course also, but anyway. So I want just to mention something that is now fascinating and also, intriguing for many of us. So there is this relation between the notion of column exchangeable arrays, jointly exchangeable arrays, and random graphs. A random graph of vertices V and D is exchangeable if its distribution is invariant under every permutation of the vertices or equivalent to the adjacency matrix is jointly column exchangeable. And there is beautiful and fascinating theory on large graphs and graph limits developed by Laszlo Lovac, a great mathematician, and many great collaborators. That has strict connection with Aldous Hoover-Kallenberg representation. And this is well explained by, for example, in Diaconis and Jensen, and also in the recent review by Orbans and Roy. And there, there is an issue that is now debated and hot, that despite many models, also 1 minute, are exchangeable, however, exchangeable graphs are either dense or empty, while real networks tend to be sparse and show power law behaviors. And so Orbans and Roy, for example, says, that means that the exchangeable models we use for networks are not realistic. And this has stimulated, this problem has stimulated very interesting work, Aron and Fox and others. So again, I hope that there will be talks in this conference, there will be on these contributions. I just finish with a little, what is the English expression, 2 cents. My way of looking at this is related to the idea of randomly reinforced preferential attachment that I mentioned, CID or quasi-CID. So if I introduce a system of randomly preferential attachment, I can model selection and competition or other forms of non-stationarity in the graph evolution. For random graphs, it is known that there is an analog of convergence of the empirical distribution. In my 2 colors soon was the convergence of the uncomposition to zeta and to theta. Here is a notion of checkboard, say it's an analog for random graphs of convergence of the empirical distribution. So if, I'm not sure, to my knowledge, I don't have a clear yet, maybe I'm not expert enough of the problem, but I don't have a clear analog of convergence of the predictive distribution. But if we have so, then we can use all these predictive schemes that I've been bothering you with. And maybe in this setting, maybe there are implications. Some work already exists, but my idea is that this could be a way of modeling an evolution of the graphs and using results, as I said, about show that we indeed have an exchangeable limit, but on a set of dominating vertices. And that's just a conjecture. Maybe in this conference you will give me comments or just say it makes no sense. And that's my last slide. Thank you very much.